All right, so for this example problem, we're given a bar attached to a wall. It has a 2,000-pound force pulling against it, and we're given the change in length is equal to 0.1 inch, and we're given the original length. The problem then asks us, determine the stress and strain, and then is the bar in tension or compression? So for our given values, we have that the force acting on the bar is 2,000 pounds. We have the cross-sectional area of the bar is 20 inches squared. And just a reminder, that cross-sectional area, it's if you took something and cut the bar along that way, and we're looking at the end, right? It's that area that you see from the end, right? And they're saying that area is 20 inches squared. So maybe it's not a circle, maybe it's a square. They gave us the area, so we don't have to do any calculations for it. So that's nice. We're also given the original length of the bar was 3 feet, and that the change in length of the bar due to the force is 0.1 inches. We're then asked to find strain, stress, and is it tensile or compressive? Right, so for our solution, we know that normal stress is equal to force divided by area. We're given a force of 2,000 pounds, and we're given an area of 20 square inches. So it's pretty easy to show that the stress is 100 psi. Similarly, for strain, our base equation is that the change in length divided by the initial length is equal to the strain. So we're given both of those right on. So 0.1 inches divided by 3 feet. We have to do a little bit of unit conversion to make sure that everything cancels out. 12 inches per foot. Make sure our railroad tracks worked. They did. And we get that the strain is 0.00278. Now notice strain is a unitless value, right? Every time you do strain, you should come up with something unitless. And that makes sense because we would think that the strain would be the same whether we were trying to figure out what is it in inches or what is it in feet. It's just a relative change in dimension for our object. And then lastly, for tensile or compressive, we can see that the force is pulling against the end of the bar. The change in length is positive because it's getting longer. That means you are essentially, if you imagine all of your little atoms in a matrix with their atomic bonds between them, you're pulling against them, making them come further apart. So that's tension. So the bar is in tension. All right, and that's all there is to this one.